time because that's what always happens. Let me change a bit the sign convention I used last time so that things are consistent, at least within the talk. So there's one little thing. So here I started with this differential graded algebra where the differential was given by insertion of one form. Let me change that to minus this. This is just a harmless minus. It doesn't really change anything around here. Maybe, well, there is minus here, but 0 is 0. So that's not an issue. And maybe here we get another sign. Okay, so the reason for that sign is that, well, so my first attempt was good. So here we have minus, and here we have minus. So just to check whether this is consistent. So I gave you the general formula for the bracket, for the anti-bracket, with this notation where I write the derivative in with respect to the field as a formal generator on the fiber, and they write it on the right. So let's see, if I have a vector field X and the function, then from the first term, I have nothing because the second argument is a function, so it doesn't depend on antifields. It's a function, it lives downstairs, doesn't have anything on the fiber. So I only have the second term, so this is then minus. So the right derivative with respect to the antifield just picks up this coefficient. So I have x of x, and then the left derivative of f. So this is the LF over the phi of x. Of course, for well, working with just a configuration space and multi-vector fields thereon, it doesn't make sense to distinguish between left and right derivative there. So this is just the same as x of x df over d phi. Okay, so this is then minus with the action of the vector field on f. So apologies for messing up this convention. Now, why did I distinguish here with the left and right derivatives? Well, the point is that in a minute, I'm going to go to a more general situation where the configuration space itself can also be graded, manifold graded vector space. But before that, let me make a small observation. So this bracket allows us to write our differential. So I showed it at the beginning as well, as almost a derivation, okay? And so this is going to be, let me start the next lecture. And sorry, this should be lecture 4. And I'm going to copy some of this information. So I'm going to copy this formula for the bracket. So let's start with this here. Maybe a bit smaller. Okay, so I'm starting with this one, and observation. Is the following. So this bracket can be used to write delta of x. So that was minus the insertion of the LX. And from the definition, this is minus, and here we have the LX. And again, by definition of this Euler-Lagrange derivative, this is minus dl of f over d phi of x contracted with the vector field, and F is identically 1 on the support of X. So we can now use this bracket formula again, and we can write this. So this can be then written as the bracket. Now I have to do this the right way around, the bracket of X with L of F. So this is exactly that last bit, where F is identically 1 on support X. So one is used to the fact that, in nice cases, your differential would be, well, it's given in terms of the brackets somehow. Here it's almost the case one only has to manipulate these supports so that everything works. And I'm just going to use a notation which kind of forgets this bit with the test function. So I'm going to typically just write X bracket L, but this is to mean that I evaluate at the test function, which is equal to 1 on the support of X. So that's for future reference. And this is very nice because instead of giving the differential, I can here just give this Lagrangian. So the Lagrangian knows everything about the differential. Okay, so now I want to comment on what we're doing in the situation where we have symmetries. So I'm going to use that structure to address that. So in the situation with symmetries, and this we described in terms of our differential complex as h minus 1 is non-trivial. So then what we do, we replace our configuration space that we started with something graded, with a graded vector space. So we replace E with some graded vector space. And I will denote it E bar, so it's an extended configuration space. So we add more field configurations. So this is extended configuration space. And for example, let me give you a standard example, which I will comment on. For example, for Young-Mills theories, so gauge theories with some gauge group G, I can now take its Lie algebra, take fracture G, so the Lie algebra of that group, and define this extended configuration space as E in degree 0. So the original one plus, now in degree 1, I put the copy of this Lie algebra. So to give you some more physics context, this space is interpreted as the space of ghosts. So here, these odd generators are called ghosts. Oh, sorry, I'm really messing up the signs. So this is +1, not -1. Apologies. Okay. Yeah, so odd generators called ghosts. silly name, but okay. Well, the sort of rationale behind it is that they're auxiliary non-physical variables. So ghosts. Okay, and well, sometimes this is it. So in the case of Yang-Mills theory, this is all the extension you have to do. Sometimes you have to carry on. And yesterday there was a question about ghosts of ghosts and adding higher degrees. And this might be necessary as well. So that's one extension I'm doing. So I'm extending this configuration space with some graded variables. And another extension, I extend the Lagrangian to, well, something I would denote Lx. And the reason for this is, well, both these extensions have to work in such a way that my differential, my chain complex I wrote here, right? So my chain complex here, after that extension, after adding new variables and adding new terms to the differential, that this becomes a resolution. So observe that the way I describe things, the fact that we have non-trivial symmetries makes the -1 cohomology non-trivial. Now, by this clever extension, we are essentially killing that cohomology. So then -1 become trivial. And then we look at higher degrees and see if we need more variables and more terms in the differential so that we can make this in the end into a resolution. So let me come back to the main plot. So we extend the Lagrangian, which by what I just said, essentially extends the differential. So we extend the Lagrangian, and hence the differential so now my new differential is going to be denoted by lowercase s. So s is defined as the bracket with the extended action. There is a question.
Yeah, I have a question, Kasia.
Yes.
You don't see me, but I'm here.
Hi.
This is Chen Chang.
Yes, I recognize you.
So can you I saw this something like first I guess you are resolving L inverse 0 in a derived way.
Yes.
Then you're adding this symmetry inside G1. You're adding maybe it's go.
No, I'm not really adding them. So they are there. So I start so in Yang-Mills theory, this
they are there.
Yeah, this differential
the resolution, right?
Yeah, so this wouldn't be a resolution for Yang-Mills.
Yeah, if you don't add these guys.
If I don't add these things, yeah.
It looks to me as some sort of symplectic reduction, like you first take inverse 0, then you add symmetries, namely taking quotient. But you know, like but I want your confirmation, like that's really something going on, because I guess that's also related to what Martin asked yesterday. Like we are really familiar with the Hamiltonian picture. The Hamiltonian is really a moment map, right? Then it's a symplectic reduction, but now it's not Hamiltonian, it's this Lagrangian. But what's going on classically, we know that Lagrangian usually are not moment maps, right? But it still looks something like a symplectic reduction. What's really going on over there?
Yeah, so one thing to notice is that here we have an odd symplectic structure. So here is maybe a note, by the way. So we have we have an odd symplectic structure. And this is, well, essentially on this space, on this odd cotangent bundle, right? So we have odd cotangent bundle. Yeah, and the symplectic structure is then d phi wedge d phi dagger. So, I mean, this is a bit formal notation, but yeah, we have these antifields on the cotangent direction. We have fields on the base, and then the symplectic structure, the odd symplectic structure, is given by this. So the analogy with the Hamiltonian formalism is actually not that bad. So one can translate many things this way, but you, in addition, well, you have some graded geometry going on. So that's the main difference.
In this odd case, somehow the Lagrangian is the moment map.
Probably, yes. Sorry, I'm not so familiar with the Hamiltonian side of things, but that's very likely.
You are doing something like L inverse 0 modeled by some symmetry.
Yes.
Applying a symplectic structure on this quotient.
Yeah, so I've seen ways of like thinking about this as a symplectic reduction, but I'm not that familiar with the sort of yeah, odd symplectic geometry side of things. But yeah, there's definitely a lot of literature in that direction. So I think people have been thinking about it, and probably yeah, one can find the precise analogy.
Okay, great. Thank you very much.
Thanks for the question.
So
yeah.
So are we? Is this a gauge symmetry? Are we gauging this symmetry? I'm not sure.
We're not gauging. I don't use it as a verb, but it is a gauge symmetry. Yes, Yang-Mills theory is gauge theory. Yes.
Yeah, because I mean you're talking about symplectic quotients and everything. So
yeah.
But I mean we don't have to, right? Or am I confused?
No, we have to. So okay. so let's say in Yang-Mills theory, this so I'm writing now this complex. So in Yang-Mills theory, H-1 becomes non-trivial.
Okay.
Okay, so then, but however, I want a resolution. So for reasons that I will try to explain later, I want this complex to be a resolution. So I have to, well, essentially add some generators in degree 2 that are going to kill that cohomology, right? So I'm just going to call it sim because these generators come from the symmetries. And adding those generators can actually be encoded in extending that configuration space and extending this differential. So the generators I add here, they also well, create their shadows on the cotangent bundle. So these generators that come here are cotangent vectors to the generators I had there. And sorry, so this should be, oh, so this is degree -2. This is -1 shifted. So the generators I have in degree 1, then I take the inverse, so -1, and then -1 shifted. So this is -2. So the cotangent vectors to this land in degree -2, and then I use them to kill the H-1 cohomology. Okay, and then I continue. Now, so for Yang-Mills, this is it. Then this becomes a resolution.
Yeah.
But for other theories which have the so-called ghost of ghosts, which have redundancy, so they have relations between symmetries, this might go on for a while.
Yeah, so but is H-1 now the collection? I had the impression that it was literally the collection of infinitesimal symmetries.
Yes.
Okay.
But now I essentially put in degree 1 a sort of a copy for each symmetry that then cancels that component in V.
I think I'm just fundamentally confused. If I have a complex scalar, then it has a U1 symmetry, and I can decide.
Oh, but right, yes, okay.
I can decide to gauge it, and then I have to add another field and integrate over it.
Yeah, I don't know what does it mean to decide to gauge it. I'm just looking at the theory as it is.
Yeah.
So I have a Lagrangian. I can write this chain complex, and then the cohomology is what it is.
Yeah. So it's just some redundancy in the description that you want to get rid of.
Yeah. So these are local symmetries, right? So
yes,
in particular, gauge symmetries are local. Sure. So these local symmetries just pop up in this complex.
Mm-hmm.
And yeah, so I don't have much choice there. So if there is a redundancy in the description, which shows up in the redundancy in the solutions of equations of motion, if there is redundancy, then I have to kill it. So I have to add those generators and continue.
Okay, I think I understand.
But I don't, well, I mean, what you're talking about is a bit more subtle than this. But I'm not sure if I completely understand it in my setting. So to gauge or not to gauge. I don't. So with this, I don't really have a choice.
Yeah.
But on the other hand, from the strictly mathematical perspective, right, the original complex was as good, right? I mean, it had non-vanishing higher cohomology, so what? I could also play with that one. The reason why I don't is because I want to keep to some sort of physical interpretation to that whole business. But yeah, I guess if you're just interested in studying such structures, you can also maybe add these generators more freely, whether you need them or not. So that's my conjecture. They probably play the games with gauging or not gauging if you're sort of fast and loose with physical interpretation. So okay, but that's very good. So
this helps.
And this is a very sketchy way of doing this. I refer to my paper on quantum BV, where I write this down in a bit more detail. So here is just really crash course into gauge symmetries. So just to summarize what I said, so I want this complex to be a resolution. Okay, and sort of one systematic way of doing this is by extending the configuration space, extending the Lagrangian, so that it's again a bracket with the extended Lagrangian, so the differential is the bracket. And here I can again recover my original differential delta. It's still here. And there's going to be a higher order term and possibly even more. So this is now expansion in antifield number. So this is, let's see, I need a bit more room. So this is antifield number. So delta is decreasing the antifield number. So a vector field has an antifield number 1 because it has one antifield generator. A functional is 0. So this is -1. And the second term is degree 0. And potentially you can have higher order terms in antifield number. But the basic structure is that you have a differential in degree -1, a differential in degree 0, and you can actually write this as a bicomplex, and S is the total differential. So Okay, so we can also write this. Oops. Antifield number is the number of those odd generators. So let me just go back a bit. So the question was about Antifield number. So here I want to write vector fields in terms of these formal generators, phi double dagger, and these formal generators are interpreted as antifields. So this is the note on the margin. So the antifield number counts the number of these odd generators, counts the number of generators. Okay, so it's again another bookkeeping device. So yeah, so we can also write things in terms of a bicomplex. So with delta. Okay, so let me write this more precisely. So with delta, a horizontal differential, with gamma, so this is this new term that arises if we have symmetries. So this is vertical, and S is the total differential. Okay, and now we build things in a way which makes delta into a resolution. So this is a resolution. So an important fact is that if I want to compute H0 of S, this turns out to be, well, on this space, BV. So this turns out to be H0 on H0 of, so first I take the homology of delta, homology or cohomology. So I'm going this way, sorry, so this is still going to be cohomology of delta. This is a resolution. So if I do my spectral sequences game, then there's just, well, this contribution. And so I take H0 of delta first, and then I take H0 of gamma. So this way of describing the cohomology of S in terms of that of gamma and of delta is something which is specific to, well, the situation where delta is a resolution. Let's see what we have. The ghosts are in the configuration space. So the question is, are the ghosts or their duals in F or in V? That's a good question. So let's go back to the ghosts. So here, when you take the space of functionals, so functionals on this, so this would be our old functionals, right? So let's say C infinity of E, complex valued, some kind of completed tensor product with the dual of the exterior algebra over the dual of G. So yes, the duals of the ghosts are now in the space of functionals on E. So the space of nice functionals on E contains in particular the duals of ghosts. Now, if I want to take the odd cotangent bundle, so again, I'm going to use the privilege of having the tablet. So I'm going to move this down a bit.
Sorry, what's this
Yes.
BV in your cohomology? Cohomology of S, BV?
BV is the space of multilocal.
Oh, that's your resolution thing, or?
Yeah,
Okay.
multilocal functionals.
Okay.
On the odd cotangent bundle. Okay. And that was just describing the odd cotangent bundle in more detail. So yeah, so now the odd cotangent bundle, yeah, I should also say that of E, so this would be, well, on the base there is that bit, and now I'm going to take the variables on the fiber. So this is E dual -1. So this is where the antifields are. Well, yeah, so antifields are going to be everything to the right. So this, and from the ghosts, I have G in degree. I don't know why I keep on writing -1 here. It should be 1. And then here I have G -2. G dual. Okay. Apologies for that. So these are antifields. And in particular, these generators here appear in degree -2 in order to kill the cohomology in degree -1. So they appear, well, they appear in the image of the differential. So you enlarge the image by exactly what was before in the kernel. So you kill the cohomology in degree -1. Okay, so that is the menagerie in the Young-Mills theory. So you have your basic fields, you have ghosts, you have antifields of your basic fields, and you have antifields of ghosts. Just to confuse you a bit, what people call anti-ghosts is not the same as antifields of ghosts, because they came up with the name before a consistent framework was out there. So one has to be a bit careful with reading that literature. It gets wild. Okay, yeah, I will add again some references to this story that you might want to read a bit more about it in concrete examples. Let's see. Any more questions? Okay, so yeah, so that's the classical theory. Oh yeah, maybe I should also add why did I want this description in terms of gamma and delta. So physically, and again, this is before, because I'm so a bit bound with the bonds of physics. So this has the interpretation of being functionals on shell, so on the space of solutions. So functionals. So yeah, going on shell. On shell. So taking functionals on the solution space. Okay, and this part, so taking H0 of gamma, has the interpretation of taking the space of symmetry invariant variables. And I'm not attempting to, sorry, I'm not attempting to explain it in detail because I really want to say something about quantization since the whole school seems to be about it. So yeah, I would send you to some references, but and this is not even the end of the story. So one typically also has to add even more variables and make some quasi-isomorphisms. So apply quasi-isomorphism to the resulting complex so that you can perform gauge fixing. So there is more technology behind this, which is only marginally relevant for quantization, because really, like, whatever happens on this classical side of things, what you get out of it in the end, there is some graded space, there is a functional on this graded space, there is a differential, and this is all you have to worry about. So you know, you can have a friend who gives you this data, and then you can go ahead and quantize it. So you can treat all of that horrible mess as a black box. So the output from the classical theory is, well, some graded vector space. So this is this extended configuration space. Okay, there is this Lagrangian, extended Lagrangian, which gives us the differential as bracketing with this Lagrangian. And now for the analytical part of this to make sense, so this Lagrangian we want to write as the quadratic part plus the rest. So this is quadratic part. And then this quadratic part, we can also expand in antifield number, in, well, typically into two terms, but yeah, so let's say that this is no antifields, and this is the rest. And because in the end I want some, well, I want to be able to construct these this pious bracket, this zero shifted Poisson structure I told you about. So I want to play the same game I did for the scalar field. I need to make some assumptions on this L0. So assume that L0, 0, so this is the quadratic no antifield part of the Lagrangian, that the second derivative induces a normally hyperbolic operator P. So whatever mess happened in between, in the end, I want this very slim number of data. So graded vector space, Lagrangian, and that Lagrangian should have in the lowest order in antifields, so the zero order in antifields, its quadratic part should give me a normally hyperbolic operator, so that I can come back to my analytical skills and construct the corresponding green functions, corresponding pious bracket, and have the tools for quantization as I know it. So, okay, so I have this P, and from that I have, now this is quadratic, so from that I have a constant Poisson bivector pi. Okay, and this is a bit of a repeat from lecture 2. So now with this then I get the pious bracket. Hello, can you hear me?
I mean, we lost you for like a couple of seconds.
Okay, did you hear constant Poisson bivector?
Yes, but there was something before that I think we missed, but I don't know if it was very important.
Oh, I don't know either, because I don't know what you missed.
Yeah,
okay,
sure.
Yeah, no, so let me then repeat what I wrote here. So we assume that the zero order of the quadratic part of the Lagrangian induces normally hyperbolic operator. Because this is quadratic part, then this operator doesn't depend on the point, doesn't depend on phi. This gives us a constant Poisson bivector, and using this constant Poisson bivector, we construct the pious bracket. So I get the pious bracket. And again, this is exactly the same construction as for the scalar field, potentially with these extra variables running around, but yeah, this is not visible on this level. Only I should mind the order. So yeah, let me just check which direction I did it. Okay, pi first. So pi d f d g. And this constant Poisson structure is what I'm going to quantize in the free theory. So this, oops, there is a question. Yes, that's the question is, does the pious bracket only depend on L00? That's right. So because this L00 has the information about linearized equations of motion as before, and this rest has the information about linearized symmetries. So that's a different part of the data. So knows about linearized symmetries. So that part plays a different role. Okay, so the next step here is quantization of the free theory. Okay, so the free theory is given in terms of that bracket. So we have the bracket, and we have the linearized, yeah, let me maybe write down this free classical theory. So P of O is the space B V of O. So this is multi-local functionals on the odd cotangent bundle. We have the pious bracket as before, and we have the linearized BV differential, which is the anti-bracket with L0. So now I take the full L0. Okay, so this is the output from the classical theory. And now for the sake of quantization, well, here I can rely on the lecture of Stefan, where he showed you how to quantize the situation with the constant Poisson structure. So I'm using deformation quantization. Deformation quantization, formal one for now. So I invoke formal power series in H bar. So the question is, why don't you include all the extended Lagrangian in the free theory? I do include all the extended Lagrangian in the free theory. So for on the level of the differential. So the free theory, is described by few pieces of data. So one piece of data is this chain complex where the differential plays a role, and the differential uses the whole quadratic Lagrangian. But the pious bracket is only part of that information. So the pious bracket only needs to know about equations of motion, and then symmetries enter on a different level. So sorry. Oh, yes. I dropped the interacting part. So let's look at this expansion here again. Right, so we have L extended is now I describe it as L0 plus V, which is the interaction. Yeah, and I'm going to come back to the interaction tomorrow, where I kind of plug it back. And yes, the free theory is where I get rid of the interaction and only work with the quadratic part L0, and then yeah, I have these two terms, one with no antifields and the rest. Okay, so now I stripped some of the structure I had, but I'm going to put it back step by step. So, well, the way I know how to quantize things is unfortunately perturbative. So I really know very well how to quantize the free theory. So how to quantize constant Poisson bivector. So I'm going to do things in two steps. So first I'm going to quantize the free theory, and then I'm going to reintroduce the interaction using perturbation theory. So this is the strategy. Okay. So yeah, so quantization of the free theory is simple, relatively simple. So I define a star product on my extended space of functionals. And well, I'm using this exponential formula that Stefan already showed you. So there is a formal power series in H bar, and I take derivatives of F and G. Sorry, the other way around. So here I have some integral kernel, and then I contract it with derivatives of F and G. And this integral kernel W, so this is what Stefan denoted by lambda. This is the antisymmetric part is this Poisson bivector, but it also has symmetric part. So this guy is a symmetric part, so it doesn't change the commutator. Okay. And now this choice of W has to be done in a specific way. So, well, the choice of W is essentially choice of the symmetric part. So choice of this symmetric part has to satisfy the following conditions. So I'm just going to list them to finish. So W has to be a solution for this differential operator P of our free theory. So W is a bisolution for P. So in other words, if I plug into W P on a test function in either argument, then I get 0. So this is being bisolution. 2, W has to be positive definite as a distributional kernel. Positive definite. Okay, so this is saying that if I take F complex conjugate and F plugged into W, this has to be greater or equal 0. Next, so next one is analytic, and I'm just going to state it and send you to some references. So the singularity structure of W has to be not too bad. So there is a condition on the wavefront set of that. So condition on the wavefront set. Sorry. Wavefront set of W. So this is called microlocal spectrum condition. And finally, so, and this is, again, we are coming back to this differential as 0. So, sorry, I have to mute myself for a second. Okay, my clock finished. So another condition I can state that S0 has to be a derivation with respect to star. So this is actually, whoops, another question. Oh, P is defined here. So this is the operator induced by this second derivative of L0. So second derivative of L0 gives you some integral kernel, and then this induces a differential operator. No worries. And okay, so because but this is now a good point to recall that, because I defined S0 as the bracket with L00 plus theta 0, right? So it has these two elements. You can check that by definition, because W is a bisolution, then it is a derivation if you just take the bracket with this first part. So let me just make that a remark. So and B. So from 1, it follows that bracketing with L00 is a derivation with respect to star. So the only thing that is a sort of non-trivial requirement is that bracketing with θ0 is also a derivation. So non-trivial requirement is that bracketing with θ0 is a derivation as well. And this can be formulated as a condition for this integral kernel. So can be formulated as a condition, slightly messy condition for W. Okay, so we have these 4 requirements for the choice of the integral kernel for the star product. Now, the job, of course, is to show that such things exist. And this is the job that has been done by other people mostly. So we can just go ahead and use them. That is very anticlimactic. That actually finishes the quantization of the free theory. And because Stefan gave such a beautiful account of all the subtleties, I don't have to say anything more, I hope. And tomorrow I want to start from there. So from this quantized free theory, and remember that I also have an interaction to worry about. So tomorrow, finally, I'm going to construct the interacting theory. Thank you.
Thank you very much for your talk. So there have already been many questions, but are there any more?
I see that Layli is asking.
Yeah, I raised my hand. Sorry, again, a stupid question about notation. I think I cannot quite spot what is θ0.
Oh yeah, that's sorry. That's here in that part. So
okay,
so
yeah, sorry, because
yeah, so the quadratic Lagrangian splits into 2 bits. So one is with no antifields, that's L00, and θ0 is the rest.
Yeah, thank you, because I didn't see the.
Yeah.
Thank you.
No worries.
Yeah, I also have a question.
Yes.
So in your lectures, you explained very nicely the role of the Lagrangian and basically derived all the equations of motions and symmetries and everything just from the Lagrangian.
Yes.
But now we also have this pious bracket. What's the reason to introduce it? What's its meaning? Why do
Pious bracket.
if it seems that all the physics is in the Lagrangian, so what's the role of this bracket?
Well, I mean, yeah. So the pious bracket is obviously also constructed from the Lagrangian or bits of it. So because it's a Lagrangian framework, everything does come from the Lagrangian, including the bracket. Well, so this is, just a Poisson bracket of the classical theory. So I understand the classical theory as the Poisson algebra, and this is the Poisson bracket of that Poisson algebra. So yeah. So.
Oh, but sorry, but then I mean, there is a Poisson bracket that you use for the equations of motions, the Schouten bracket.
Yeah, but they are different. They have different roles. So first of all, the Schouten bracket is -1 shifted, and I want a 0 shifted bracket for the definition of the Poisson algebra. So this in this way of viewing things, your classical theory really has honest to goodness Poisson bracket, which is zero shifted. This well, one can, these things are connected. So instead, one could say, well, we have this anti-bracket plus extra structure. And from that follows this pious bracket. But these are, yeah, these brackets are related, but they play a different role in the structure. So you can think of this as a situation where you have two brackets really. So you have the zero shifted and -1 shifted. But these are not independent structures.
Yeah, okay. To me, it looked like the pious bracket was coming out of the blue, whereas the other one was kind of very good motivated by
Well, no, the other, so pious bracket comes from the Lagrangian, comes from the dynamics of the theory. It comes from the dynamics of a specific theory. The anti-bracket comes from the geometry. So this is, so, well, you can say it's purely kinematic. It knows nothing about the dynamics. So you can construct the pious bracket from the anti-bracket, feeding it some information about the dynamics. So pious bracket has dynamical information, anti-bracket doesn't. It's common for, you know, all the theories that are on the same space of configurations. In that sense, of course, it's geometrically, you know, this is what's there without specifying any dynamics. So you can say it's more natural because yeah, you have it even without the dynamics.
Okay, well, thanks.
So all the, oh, there is a hand.
I have a question. Can I ask a question? Okay.
Sure.
This deformation quantization gives the same result as the normal canonical quantization?
Yes. Yes,
my
yes.
question is the relation with the canonical quantization.
Sorry, what?
Yeah, my question is the relation with the canonical quantization.
Okay, yeah, that's a good question. Let's see. So yeah, well, in the end, what you construct is some star algebra, and you know, the one you construct from the canonical quantization is isomorphic to the one you construct this way. So you can see it very explicitly that, well, yeah, I might come back to this example maybe early tomorrow, that you get the same commutation relations. You can identify observables in this algebra with the observables you would get by canonical quantization, and then you have yeah, you have the same commutation relations. So this is an equivalent way of quantizing things. With deformation quantization, you can quantize more observables somehow, right? Because you don't, it's somehow the way to address the ordering problem. So
yeah, in the canonical quantization, we need the normal ordering.
Yes.
Yeah.
Yes, and this, so in a sense, this choice of W here, of this integral kernel, is the choice of normal ordering in canonical quantization. You can view it this way. So choosing different ordering prescription would change this W and would lead to an equivalent star product.
That this information is included in W. Right?
Yes. Yes.
Thank you.
And I see the question on the chat. Yeah, so the question is, in QFT textbook, you use the Lagrangian to cook up canonically conjugate fields, and then you quantize them to commutator relation. Does the pairs bracket correspond to that? Well, yes, yes, that is correct. So the pairs bracket is for linear fields coincides is with the commutator function, right? So if you have linear fields, then and this also partially addresses the other question, right? So if you have linear fields, so sorry, just this one remark, and then you compute the star commutator of linear fields for two different test functions. So then that catches only the antisymmetric part of W. So, well, there will be the zero order term, which is less relevant, plus IH bar. And now I have pi contracted with F tensor G. And this is exactly the pairs bracket of these two linear observables. Yes, so and this is the commutator that you would also get from this slightly dodgy procedure usually done in physics. So yeah, it reproduces the same commutation relations as the usual approach.
So this is exact, or is it up to higher orders in H bar?
This is exact. Sorry, this is exact because this is linear fields. So you have the zero order, no derivatives, first order one derivative, no more orders because derivatives vanish. Oh, actually, sorry, this is not here because it's a commutator, so this cancels, right? Because yeah, so from the commutator, that zero order term cancels. So that's all there is.
So just another more question on this pairs bracket. So how important is for you that you have a cotangent bundle? So
Yes.
can any -1 shifted symplectic manifold?
Yes.
Or so in order to have the pairs bracket, you need a cotangent bundle, or can be an arbitrary?
No, that you don't. so the pairs bracket you can construct independently of this whole formalism I'm introducing. So in the original paper of pairs that I should also put in the references, he just constructs it in purely Lagrangian framework. So you just have Lagrangian, and then you have your classical observables. He's also working on shell, so on the space of solutions, and that's all you need. So yeah.
So is this pairs bracket what some mathematicians also call a derived bracket?
No, the antibracket is the derived bracket. Pairs bracket is a different bracket.
And maybe just the last question. So there are the other kind of models like, AQFT that are just topological.
Yes.
So can you make solid theory similar to this one with this kind of topological background, AQFT?
Well, AQFT is just well, a certain formulation of BV, right? It's a yeah. I mean, it's essentially a language, right? So yeah. So the well, maybe the problem or a challenge here with topological theories is that the way I described the quantization here really relies on having a dynamics of a specific type. So my dynamical equations are given by normally hyperbolic operators. This is a very strong assumption on the dynamic side. So that wouldn't apply to topological field theories, I think. So then you have to do something different. But yeah, like a lot of these structures, like the Antibracket, obviously do exist in that setting. But yeah, the dynamics would be different. So the quantization would be different.
Is what doesn't appear in the topological.
Sorry?
I think that the pious bracket is the one that doesn't appear in the topological.
Yeah, it doesn't appear because it's really tied to the dynamical information of a specific type. Yes.
So all the way in presentation 1, you told us about AQFT, and then you argued that we want to do a perturbative theory because there are only free theories in AQFT. Yes. And you promised me to define free theories.
Yes.
And now you did, but I'm not super happy, I think. So
it's less exciting than you thought. Okay. Why?
Well, so I expect. So in AQFT, do you also do things with powers in H bar?
No, this is pAQFT. So,
yeah, exactly.
Yeah. So
yeah, no, I'm asking about the free theory. So then you don't
the free theory you can also do non-perturbatively.
Okay, so what's the comparison?
Well, so first of all, what this is also relating to what Stefan is talking about with the convergence. So for example, if I restrict to polynomials, this is kind of obvious that this becomes just, all these series are convergent because they have only finitely many terms. H bar can be a number. I can do Weil algebra. So those functionals I can take to be exponentials, and then also all these things become convergent. So so in free theory you can do more by specific choice of observables, by specific choice of topologies, because I have said nothing about the topologies on the space of functionals. And I'm kind of bought into this this way of thinking that, well, yeah, Banach is great, but these locally convex topologies are actually more flexible. So I can topologize these spaces of functionals with some locally convex topologies, as Stefan said, and then get some convergence in the free theory. The reason why I didn't focus on it is because I have no idea how to do it for the interacting theory. So I will just let that sit. But yeah, in free theory, you can do much better. This is just to lay ground for the interacting theory where I cannot.
Yes, okay.
Okay.
Any more questions, comments? Doesn't look like it's the case. So then I guess we can thank Kasia again. Thank you very much.
Thank you. And tomorrow interaction. Finally.